So now we have the equation, and we have to determine whether or not it's symmetric about the x-axis, the y-axis, the origin, or none. So let's start with the x-axis first. And in order to determine if we have x-axis symmetry, we're going to plug in negative y for y. Because remember, the definition of x-axis symmetry said that if xy is a point on the graph, then x negative y should be a point on the graph as well. So now when we plug that in, we get negative y equals 3x to the fourth over x squared plus 1. And this is not equivalent to the equation we started with, right? And you can pick x equals 1 to convince yourself of that. But it has to hold for all pairs x and y that satisfy the first equation, and this doesn't. If we check for y-axis symmetry, we're going to do the same thing. We're going to plug in negative x for x. And we end up with y equals 3 negative x to the fourth, remember your parentheses there, over negative x squared plus 1. And now this is going to simplify to 3 times negative x to the fourth is the same as x to the fourth, right? Because a negative raised to an even power is positive. And for the same reason, that negative x squared is going to simplify to just x squared. And this is equivalent. So we don't have x-axis symmetry, but we do have y-axis symmetry. All right, and now there's only one more left to check. We have to check the origin, because you could potentially have more than one type of symmetry. For the origin, we are going to plug in negative x for x and negative y for y. So what we're going to end up with is negative y equals 3 times negative x to the fourth over negative x squared plus 1, and that will simplify to negative y equals 3x to the fourth over x squared plus 1, and we've already said that this is not equivalent. So we do not have origin symmetry. So the only symmetry we have here is y-axis symmetry.